What's up? My name is Matthew, and in this video we're going to talk about nth roots, like square roots and cube roots and 38th roots, even roots, odd roots, and then we're going to take that a little bit further. We're going to look at some radical functions, we'll evaluate some radical functions, and we'll talk about how to graph those functions. Let's have a look. The first thing that we need to look at in this topic is the definition of a square root. And most of you, if not all of you, watching this video know what a square root is already. However, we can say that b is a square root of a number a if b squared equals a, for example. Well, let's look at the first example. We'd like to identify the square roots of the real numbers. So the first number we want to take the square root of is 25. But what I want you to try to remember is that the square root of 5 has two answers. One of them is positive and one of them is negative. So I would say that the answer for our first problem is, we could say that the square root of 25 is plus or minus 5. And if you remember the quadratic formula, which says x equals the opposite of b plus or minus the square root of b squared minus 4ac all divided by 2a, the plus or minus in that formula comes right before the square root symbol. And that is because whenever you're taking the square root of something, unless it's 0, you do need to be mindful of the possibility that you should be utilizing the negative answer as well as the positive. So the square root of 16 is plus or minus 4, and the square root of 49 is plus or minus 7. And part D says the square root of negative 4. We're not going to work with the square roots of negative numbers. My students who are in this intermediate algebra class many of them will be working with square roots of negative numbers in the following semester when in college algebra, and the square root of negative 4 will equal plus or minus 2i. So for those of you who were thinking, I know the answer to that one, if you said plus or minus 2i, you were correct. But in this section and in the course that I'm teaching that these notes are made for, we're not going to be working with imaginary numbers. I did have a weird technical difficulty where when I took this Word document and I saved it to a PDF, somewhere in that process, every one of these things, like the square root of a or the square root of 25, all of those were like created with an equation editor, and then they get converted to these little images, and for some reason all of the images started appearing twice. So I went through and I deleted most of them, but obviously I forgot a few because here it says the square root of a and negative square root of a and square root of 0 equals 0. All of those are appearing twice. I'm not sure why, but so we can disregard these and let's just focus on one instance of those. All right, that was a little sloppy. I can do better. Because I don't want to get rid of too much. Like I want that negative sign and I want that entire square root symbol. And all right, there we go. Not beautiful, but it works. Okay, so here, simplify the square roots if possible. We talked about the square root of 25 already equaling positive or negative 5. The square root of 0.81, be careful, some of you may be thinking 0.09. In fact, it's plus or minus 0.9. And if you punch that into a calculator and square it, 0.9 squared, you will get 0.81. Now, in part C, the negative is outside the square root symbol. We're not taking the square root of negative 36. We are negating the square root of positive 36. So maybe you're thinking, oh, that's interesting. The square root of 36 should be plus or minus 6. And then if we're negating that, so does that mean the answer is negative or positive 6? Depending on the context of the question, that negative sign might be pressing you to only use the negative version of the answer, but in this case, I'm going to say that the answer is still plus or minus 6. And if you'd like, you could include this negative sign in front of here and then throw another equals in there and still list your final answer as plus or minus 6. I heard a little scratching at the door. I'm going to see if I still have a visitor. Hello? Oh, hello. She only wants me to open the door for her. She doesn't want me to. Do you actually want to hang out? Come in and say hello. This is an unusual guest we have. Usually, my little rugrat, Sophie, comes in for a visit. But this is Luna. Can you say hi, Luna? Let's make sure you're in focus. Oh yeah, you're beautiful and you know it. You're also looking particularly grumpy today. Hi. All right, shall we get back to work? You go curl up inside of a bag or something, all right? Okay, see you later. Luna. When you're taking the square root of a fraction like 4 over 25, you are allowed to think of this as the square root of 4 over the square root of 25. Sometimes it's beneficial to actually split up the fraction with the radical on top and bottom like that. Or if you're comfortable leaving the radical over the entire fraction, that's fine too. Either way, you're going to get a final answer of plus or minus 2/5, taking the square root of 4 and the square root of 25 with that one all-encompassing plus or minus in front. In part E, very similar to what we just did in part D, the square root of 1 is 1, the square root of 9 is 3, and we still have this plus or minus in front of it, even though there's a negative outside of the radical. Again, just be careful of the context of the question. If it's a word problem, that negative sign could be encouraging you to give just a negative answer. In part F, and we're going to talk about this a little bit later in this video, we're taking the square root of a negative number here. I already said that in a subsequent course, your answer for this might be plus or minus 2i. In this course, in an intermediate algebra course, we're going to typically list our answer as undefined. At least in this course, the answer is undefined. You don't have to put plus or minus undefined. Part G, this seems kind of silly to be taking the square root of 1. Isn't the answer just 1? But it's not. You still have to include that plus or minus symbol. The only time you don't need the plus or minus, other than when the answer is undefined, is when you're taking the square root of 0. And the square root of 0 is 0, because 0 squared is 0. Now, square roots aren't all there is. We can go beyond the square root. We can talk about the nth root. And this is a little, I don't know if it's helpful for you to read that b is an nth root of a if b to the n equals a. But as we look at these two quick examples, that statement might make a little bit more sense. 2 is a square root of 4 because 2 squared is 4. Squared, square root. Let's look at the second example. 2 is a third root, or a cube root of 8, because 2 to the third, or 2 cubed, is 8. So we see if we're allowed to go one direction by checking to see if we can go the other direction, forwards and backwards. Here's another example of where we have a little duplication. Okay, this one of these shouldn't be here, so we can sort of get rid of that one. But the point is that the n that's right here, goodbye, the n that's right there that I drew an arrow to is called the index, and the stuff that's in red under the radical is called the radicand. And we don't refer to them by name all that often, but every once in a while, so it's good that you're aware of those vocab words. the index of a square root is 2, even though we don't usually write it. We normally just write the square root symbol, but there is an invisible 2 right there, just like you've got x to the third power and x squared and x to the first power, but we don't usually write the 1 on x to the first power. Similarly, we don't write the index of 2 on a square root, but if it were a cube root, we would have to write the index of 3. Now, here's where it gets a little detailed, a little bit more detailed than even I would like, but it is what it is. I see something else that's not supposed to be there that I need to get rid of. I'm just going to color over it with a white marker. There we go. I think that's it. Right, number 1 here tells us that if n, which is our index, you can see this n right here. So if n, the index, is greater than 1, and it's even, so we've got an even integer as the index, and the radicand, our a value, is greater than 0, then when we take the nth root of a, or I should say the nth root of a is the principal or the positive nth root of a. So let's attempt to translate that. So if the index is even, then the principal nth root is the positive answer. So just in case you're working a problem where you are asked for the principal root, your answer is not going to be plus or minus 2 in this case. Your answer would just be positive 2. So that's a little bit more vocab. Principal nth root is asking you for the positive solution. If n is greater than 1, if your index is greater than 1 and your index is an odd integer, 3, 5, 7, 9, and so on, then the nth root of a is the nth root of a, which is kind of funny. So the example here says that the cube root, or third root, so our index is a 3, we can see there. The cube root of -8 is -2. Yes, you are allowed to take an odd root of a negative number, a cube root of a negative number, a fifth root of a negative number, 7th, 9th, 11th, and so on of a negative number is okay. So here the cube root of -8 is -2. Why? How do I know that? Because -2 to the third power equals -8. So when you're working with an odd index, you don't need to worry about the plus or minus. If you're taking notes on this, that's a good little tidbit to write down. If you're taking an odd root, in other words, if your index is odd, you don't need to worry about the plus or minus. It's just going to be what it is. In this case, the answer was negative. I should mention that the third root of +8 is +2, because 2 to the third equals +8. And finally, if your index is an integer greater than 1, then the nth root of 0 is 0. That's nice. That's pretty consistent. All right, let's take a look at some examples. Part A says the cube root, or the third root of -64. So what number times itself, so a number times the number times the number, is equal to -64. Well, I don't think it's -1. -1 times -1 times -1 would be -1. Let's try -2. -2 times -2 times -2. Well, we already saw that. That's equal to -8. -3 times -3 times -3 equals -27. So we're getting closer. But every time we take a negative number and we cube it, or raise it to the third power, we're getting a negative answer, which is good. Eventually, we want it to equal -64. And the correct answer here is -4, because -4 to the third power equals -64. The fourth root of 256. If you don't know what the answer to this question is, and if you don't, that's okay, but you need a technique for figuring it out. And if that's using a basic 4-function calculator and trying 1 times 1 times 1 times 1, and you get 1, and that's not 256, then skip forward to 2. 2 times 2 times 2 times 2, well, that's only going to give you 16. So maybe you're a little aggressive and you try 5 times 5 times 5 times 5. Problem, you overshot it. That's equal to 625, so you got to back off a little bit. And you try 4 times 4 times 4 times 4, and you do indeed get 256. Now that's the principal root. Is -4 to the fourth power also equal to 256? Yes. All right, so just be careful. I suppose we could put that the answer here is plus or minus 4, unless the rules change later, which they might. So just be aware that at the moment we're saying it's plus or minus 4, but things may change. Let me give you some more answers here. The answer to part C is -1/2. And the answer to part D is undefined. You cannot have an even index and a negative radicand. You cannot have an even index and a negative radicand, or your answer will be undefined. All right, let's take a look in this yellow box. Finding an nth root of a variable expression. Okay, it's already too many words for me, right? I'm a math major. Okay, I didn't get into it for all these words. I'm going to jump down to these bullets. Okay, right above bullets 1 and 2, I see this: evaluating the nth root of a to the n. Interesting. If n is a positive odd integer, then the nth root of a to the n equals a. It looks like the exponent and the radical kind of canceled each other out, leaving us just with the a. So if we had the third root of m to the third, the answer would be m. Or if we had the seventh root of 2 to the 7th, the answer would be 2. Okay, I can get behind that. Now, what about our second bullet? If the index is even, so we've got an even index and an even power, the answer needs to be in absolute value bars. Interesting. Okay. Writing the absolute value ensures that our answer is positive. I don't want to get into the explanation of why we need the absolute value bars, other than to say that way it ensures that our answer is positive. If you look at the second example right here, this is an example of that even index with the even power. We've got the fourth root of -3 to the fourth power. Those 4s should cancel out, leaving us just with the -3, but since the n value, the index, and the power were even, we need to throw a set of absolute value bars on that -3, ultimately making our answer +3. So you can see how in a homework problem, or on a quiz, or on a test, even if it's multiple choice, if one of your answers is +3 and one of your answers is -3, if you don't commit this kind of relationship to memory, you're liable to get that question wrong, and I don't want that for you. So do take a note on these two bullets that are right below me here. You'd think I would have gotten that right there. Yeah, jot those two down, and maybe even write down an accompanying example of each one of them for you to reference later. This last example, where we're taking the fourth root of -2x to the fourth power, is interesting. There's a number in there and there's a variable, so it's an even index. The 4 on the outside and on the inside leads us to put the absolute value bars around the -2x. And then there's this additional step right here where it almost looks like we took the absolute value of the -2, made it a +2, and pulled it outside of the absolute value bars. And in fact, that's what we did. What we're trying to make happen and ensure happens is that our answer is positive. So by taking the 2 out of there, or the -2 out of there, making it positive, and then taking the absolute value of x, that way whatever x is, negative or positive, it will end up being positive, multiplied by the +2. A positive times a positive is a positive, so this final answer is definitely going to be positive. All right, that sounded a little bit like madness, but I think that you understand that this quantity right here is definitely going to be positive. So that's all we're trying to make happen there. And then this example is a slightly modified version of the one that we just finished talking about, this one right here. This next one has a -2x squared that's being raised to the 4th power and then 4th rooted. And then to the right of that, you see the absolute value bars happening. And then to the right of that, you see the -2 has been taken out and it became a +2. And the x squared, the variable squared, remains inside the absolute value bars. And then, seemingly magically, those absolute value bars disappeared. Why can we just get rid of those absolute value bars? I thought we needed to keep those there to make sure that the answer stays positive. What happens when you square a negative number? What's a negative times a negative? Positive. What happens when you square a positive number? Positive times positive is positive. X squared is already guaranteed to be positive, so putting absolute value bars on it would be redundant. That's a very little detailed niche thing that we just saw happen there, considering that we're looking at this entire course called algebra, and we've just drilled all the way down into this one tiny little thing right there. That's a lot to try to remember. So including that example in some kind of a review packet that you're building for yourself so that you do well on your next exam or quiz, that might be a good problem to throw in there, just in case you happen to run into it. At least you've seen it once in these notes and you see it once as you're paging through your review packet. And then this is a great way to get some practice in trying to remember all of those things. Here you've got the odd index, so let's look at one of these. Since it's an odd index, we don't have to worry about any absolute value bars. The final answer is going to be simply x plus 8. In number 5, we have the even index. So what we should really have as an answer is the absolute value of x plus 1. And that would be fine if this negative sign weren't here. But we do need to bring that negative sign along, and we will write it in outside of the absolute value bars. So this answer is guaranteed to be negative because of that additional negative sign outside of the square root. In number 6, we've got an even index. So we should again be using the absolute value bars, absolute value of x squared plus 7. However, as we just talked about, x squared is guaranteed to be positive, and when you add a 7 to it, it's going to be even more positive, so there's no real need to be using these absolute value bars. It's redundant, and so let's just write our final answer as x squared plus 7. Speaking of 7, in number 7, this is a little bit more tricky because this involves a little bit of extra insight. Most of you who are watching these videos are not necessarily super mathy people. And so it might not jump out at you that the number 32 is kind of a special number. 32 is 2 to the 5th power, and this index of 5 on the outside could have been a clue to you that 32 can be written as a fifth power. So what I'm going to do is, I'm not going to write 32 as 2 to the fifth. I'm going to write, oh, the iPad's freaking out. Unplug and replug. It is unplugged. It is replugged in 3, 2, 1. It's almost like that's happened before. All right, so I've got negative, and there's the fifth root, the index of 5, and underneath my radical, my radicand, I'm going to write that as negative 2 to the fifth power. Now let's start applying our rules. When we have an odd index like this, the index and the exponent cancel each other out, leaving us just with the negative 2. But there's this negative sign sort of traveling along with us. And so that negative is going to interact with this negative, leaving us with a final answer of positive 2. So we're lining up some little nuances there, some little details of this process, and making sure they interact with each other in just the right way to get us just the right answer, in this case positive 2. Number 6 is the absolute value of 5x. Number 7 is the absolute value of x plus 8 over 3. Those ones are pretty straightforward. And then we transition into something special, something that you're familiar with, the Pythagorean Theorem. The Pythagorean Theorem is a formula that describes a relationship between the side lengths of not just any triangle, only right triangles. And A and B, as we traditionally and typically know the Pythagorean Theorem as a squared plus b squared equals c squared, A and B are the leg lengths, and C is the length of the hypotenuse. Now it doesn't matter which leg gets labeled, with an A and which one gets the B, as long as those two are used to label the leg lengths. Let's have a look at an example. Use the Pythagorean Theorem and the definition of the principal square root, there it is, to find the length of the unknown side. Great, so what's already printed for us here is the Pythagorean Theorem, a squared plus b squared equals c squared, and then we have chosen to let one of the legs, which is the 9, be the a value. So that has been plugged in over here. So that says a squared is now 9 squared. We don't know what the b value is, our other leg. 15 is the hypotenuse, so that went in for the c value. And then we did some arithmetic. 9 squared is 81, 15 squared is 225. And then as we move to the right across the page, if we subtract 81 from both sides, and there's the subtraction has happened on the left-hand side, the b squared is all alone now. On the right-hand side, we have to do the arithmetic, 225 minus 81, which simplifies to equal 144 on the right-hand side. And then if we take the square root of both sides of our equation, the square root of b squared is equal to b, and the square root of 144 is equal to plus or minus 12, but since b is representing the length of the side of a triangle, it wouldn't make a lot of sense for us to say that the side length is negative 12, so we're going with positive 12, the principal square root. It will happen if you end up progressing to a pre-calculus class, which is very much the study of trigonometry. Every once in a while, your triangles might have negative side lengths, but that will be because it's trying to compel you to move in the negative direction. So the negative sign in that case is going to be talking about direction, and then the 12 would tell you how far to go in that negative direction. Number 8 is a word problem with an accompanying diagram. We have a ramp to accommodate a handicapped person, and we're being told that the distance from the door to the end of the ramp is 25 feet. And so I'm going to make the assumption that it's this length here that's 25 feet. And the height from the ground to the front door is 7 feet. All right, so it's not even easy. You know what I'm going to do? I'm going to copy this triangle out of the diagram so that it's easier for me to work with. Let's bring it out here. So this length is 25. The right angle was actually there in the diagram for us. We were told that the height is 7 feet from the ground to the doorway. What that means is that each of those steps is over 2 feet tall, which, as the son of an architect, I can tell you is almost 100% certainly against building code. I don't care where you are unless you're in the land of giants. Nobody wants to take 2 foot tall steps. Also, well, let's keep going with this before our next architectural lesson. Let's have 7 in our previous problem. The known leg length went in as our A value. Let's have 7 be the B value this time. So A squared plus B squared equals C squared. Let's pretend that we don't know what A is, so that'll be our unknown length, A squared, plus we're saying that B is equal to 7. We'll square that, equals the hypotenuse is 25. We'll square that, and we still don't know what A squared is, but I know that 7 squared is 49. I also happen to know that 25 squared, is equal to 625. And then if we subtract 49 from both sides of that equation, we find that A squared is equal to, and then I'm supposed to know what 625 minus 49 is. Well, 625 minus 50, $6.25 minus 50 cents would be $5.75. But I didn't take away 50 cents. I only took away 49 cents. So you owe me a penny. So 625 minus 50 is 575, plus the penny that you're going to give me back makes 576. There's a little mental math for you. And then we have to take the square root of 576, which you can do on a 4-function calculator, which should cost you like 99 cents, which is all you've got because you gave me that penny back. Take the square root of both sides and we find that A is equal to 24. And so that is the length of the ramp. How long is the ramp? Yeah, this question's not articulated as well as it could be. But based on the diagram that I drew, forget about the question, how long is the ramp? I would say that the length of the ramp is 25 feet. But anyway, using the ramp puts you 24 feet away from the building. How about that? Also, 24 feet of run, giving you 7 feet worth of rise. Not code. Definitely not. Definitely not. This diagram's also, I can't believe that this is to scale. It looks like a much more gentle slope than it probably really should. As I recall, the appropriate grade for a handicap ramp that's for providing wheelchair accessibility in particular is a 1/12. So with 7 feet worth of rise, 7 feet it's a lot. Your ramp would have to be extremely long. How many? So for going up 1 inch, you should have 12 inches worth of run. Oh, that's not the smoothest looking ramp there. There we go. 1/12, I believe, is what code says you should have. Now that's 7 feet up, which is, this is 1 inch. Now if it were 1 feet, if it were 1 foot, then this would have to be 12 feet long. Except it's not, it's 7. This is actually a 7, which means we'd have to take this 12 and multiply it by 7, which means it would have to be 84 feet. So in order for an appropriately and legally graded ramp that's bringing you up 7 feet off the ground, which is like almost a whole story up off the ground, your ramp would, if you got on that ramp and you took it all the way to the bottom, it would put you 84 feet away from the building. I'm going to have to modify this question the next time I use it. All right, that was a lot of blah, blah, blah. So hopefully you're using timestamps in order to skip that, but maybe you learned something you weren't supposed to. That's nice. On a sunny day, a building and its shadow form the sides of a right triangle. That's if the building's not the Leaning Tower of Pisa. If the hypotenuse is 37 meters long, I don't know how you would measure that as your initial measurement, but with a diagram, it's nice we can write the 37 in there. And the shadow is 21 meters. There's the 21. Round your answer to the nearest tenth of a meter in determining how tall the building is. Nice, this would be a better trigonometry problem, but we can definitely do it using the Pythagorean Theorem. A squared plus b squared equals c squared. Let's have a be the 21. We'll square that, plus the unknown b squared. Let's label the height of the building as b for building, equals c squared, so we have to take the 37 and square it. I didn't really need to have these parentheses around the number 21. And then you've got arithmetic to do. You've got to square the 21, square the 37, do some subtraction, take the square root of both sides, and you've got yourself a b value. Don't forget to round it to the nearest tenth. Etc., etc. This one's nice because this is a 50, and the tree is 40 meters tall, which is, that's a pretty tall palm tree. That's not like a 120 foot tall palm tree, which is like a 12-story tall palm tree. Maybe not. 4 meters probably would have been more appropriate, but I see what they're doing here. That's 40. And the question is, how long is the shadow? I can tell you immediately. Okay, the shadow's 30 feet long. How do I know that? It's not because I've done this problem before. You can do the Pythagorean theorem in order to find this answer, but here's a little shortcut, and I'm going to make sure that there's a timestamp so you can jump right to this. There are these things, these groups of side lengths called Pythagorean triples. And the first 4 triples are, remember these are side lengths of a triangle, of a right triangle, A, B, and C. There's the 3, 4, 5 triangle. Now 3 squared plus 4 squared equals 5 squared, okay? A squared plus B squared would equal C squared. These are A, B, and C values that I'm giving you. There's also the 5, 12, 13 triangle. There's the 7, 24, 25 triangle. And there's the 8, 15, 17 triangle. So the longest ones, the longest side lengths are of course the hypotenuse length. Now you can take any one of these Pythagorean triples and you can scale them up. For example, you might want to take one of them and multiply it by 10. So the 3, 4, 5 triangle would become the 30, 40, 50 triangle. And since I see that over here I'm working with a right triangle that has a hypotenuse of 50, which is the longest side on the triangle, and one of the other side lengths is 40, I know immediately that in this case the length of my shadow is 30. Can you do it using the Pythagorean theorem? Do you have to memorize these first 4 Pythagorean triples? Absolutely not. But did I know that the answer to this question was 24 without even picking up my pencil? Absolutely. Did it hurt to have the accompanying diagram? No. If there was no diagram, would I have drawn my own diagram? Absolutely. Even though the question was phrased kind of poorly. So the diagrams are good. If there isn't a diagram, draw your own. And once you've got the diagram and you label it with the given side lengths, I'm telling you, if you can use one of these Pythagorean triples, it's going to save you a lot of time, even if just for the purposes of checking your work. And let's close with this topic. I believe this is our last little subtopic. We are 40 minutes in. Wow, we're having a good time. Time just flies when you're having fun, doesn't it? Radical functions. So we're taking expressions like we had seen previously, and now we're giving them a name. We're saying that it's equal to f of x. So that's function notation. And in this example, f of x is equal to the square root of 3x plus 7. We're being asked to evaluate it for an x value of 6. In other words, we want to know what the value of f of 6 is. And it just so happens that here it says f of 6 is, and then we've plugged in the x in place of 6 here, so we're going to replace this x also with a 6. We do some arithmetic. 18 plus 7 is 25. Square root of 25 is 5. At least that's the principal root. We could have said plus or minus 5, but in this case we're just going with the positive 5. Number 11 asks us to evaluate f of x for x equals 7. Let's plug in our 7. F of 7 equals the square root of 5 times 7 plus 1. 5 times 7 is 35. 35 plus 1 is 36, so we're taking the square root of 36, and we can say that our answer is plus or minus 6. If you want to, you can come into here and put the plus or minus in front of the 5 also. I think that's the most thorough answer. Number 12. If you take the 4 and you square it, you get 16. So that would be 3 16s plus another one makes 4 16s. 4 16s is equal to 64. So g of 4 equals the square root of 64. What number multiplied by itself equals 64? I should have said what numbers multiplied by themselves equal 64. And the answers are positive and negative 8 would satisfy that statement. And very much related to the rational function conversation is to find the domain of a given rational function. In this case, you can see that the index is even. Well, let's look at this yellow box first. If the index is an even integer, then the function will be a real number. In other words, your answer is going to be a nice answer, relatively nice, only if the radicand is non-negative. In other words, your radicand, the stuff underneath the root symbol, must be greater than or equal to 0. Greater than or equal to 0. Not negative. Means it could be 0. 0 is not negative. Or it could be positive. Okay? So in this problem, we see that we have an even index. I can see the little 4 indicating the 4th root. And since 4 is even, the function is only going to give us an answer that's defined instead of getting an answer of undefined. I'd like to have a defined answer, please. The only way to make that happen is if the radicand, which is x minus 7, is greater than or equal to 0. So that's why we are setting the radicand to be greater than or equal to 0. We solve that little statement by adding 7 to both sides, which gives us this statement right here. So in order for the radicand to be non-negative, we must plug in x values that are greater than or equal to 7. And that makes sense. Plug in a 7 right here. What's 7 minus 7? 0. Can I take the 4th root of 0? Absolutely. Let's plug in a number that's bigger than 7, right? Greater than or equal to 7. Plug in an 8. 8 minus 7 is 1. Can I take the 4th root of 1? Absolutely. All right, what you don't want to do is plug in a 6 or a 6.999 even. Therefore, the domain of our function is, and here are all of the x values that are greater than or equal to 7, going from 7 up to positive infinity. Using set builder notation, that is another way to write your answer. The set of x values such that x is greater than or equal to 7. In the next example, where we're finding the domain of the function f of x is equal to the 5th root of x minus 1, because it's an odd index, there are no restrictions on the radicand. The radicand can be anything you want, so you can plug in any x value you want. So the domain is the set of all real numbers. Or, using interval notation, all of the numbers from negative infinity to positive infinity. Or, using set builder notation, you could write it like this. Or, if you wanted to be really fancy, you could write it like this. That's sometimes called a blackboard R, which represents the set of real numbers. In other words, pick any number you want. Number 13 gives us some example problems to work on. So in part A, we want to make sure, since it's an even index, it's a square root, even index, we want to make sure that 3 minus x is greater than or equal to 0. I'm going to do something unusual that you might not think to do. I'm going to add x to both sides. And then I'm going to rewrite this statement from right to left. I'm going to put the x over here and the 3 over here and switch that symbol around, and you'll notice that the x is still on the pointy side of that inequality symbol right there. And this says my x values must be less than or equal to 3. So that's from negative infinity all the way up to 3, including 3. This would be your final answer, using interval notation. Part B has an odd index, so your solution there, the domain is all real numbers. You can plug in any x value you want. And in part C, this one's interesting. It's an even index, it's a square root, so it's an even index, which means that x squared plus 2 must be greater than or equal to 0. Otherwise, we're going to get an answer that's undefined. We don't want that. But remember, when you take a number x and you square it, you're going to get a positive value, or a 0. But either way, whether you get 0 or a positive number after squaring your x value, then you add 2 to it, and it just gets even more positive. So the smallest that this could possibly be is 2. And 2 is already greater than or equal to 0. Plug in an x value of negative 5. What's negative 5 squared? Positive 25. Plus 2 makes positive 27. We went from positive to even more positive. My point is that with a square in there, it's always going to be positive, and then you're adding even more to it. That radicand is guaranteed already to be greater than or equal to 0. So you can plug in any x value you want. Positive, negative, 0, have at it. You're never going to run into a radicand in that problem that's less than 0. Therefore, your domain, the list of x values that you're allowed to plug in, is again all real numbers. Or using interval notation, the x values that go from negative to positive infinity. Here's another little duplicate incident. Let's get rid of that. All right. Write the domain of f in interval notation. So we're still talking about domain here. And we want to make sure that 5 minus x is greater than or equal to 0. I'm going to do this differently this time. I'm going to subtract 5 from both sides so that this says negative x is greater than or equal to negative 5. And then I'm going to multiply both sides by negative 1. This changes to a positive x, this changes to a positive 5, but when you multiply an inequality by a negative number, you have to switch the sign, or flip the sign. So that inequality symbol changes directions, and you end up with a domain statement that says that x must be less than or equal to 5. I'm losing control over here. There we go. Okay, I think we're back on track. Everything's working. Sorry about that. Interval notation, right. All the x values less than or equal to 5, that's everything from negative infinity all the way up to positive 5, including the 5. Now it asks us to graph the function by making a table of ordered pairs. So we want to plug in some x values, generate some y values, and plot some points. Let's choose some convenient x values that are 5 or less. Well, if I'm allowed to use 5, I'm going to use the 5 right away. And what's nice is that if you look right, where is it? No, this way. It's very tough because it's a mirror image for me. If you look at our original statement there, what's 5 minus 5? 0. That was convenient. What's the square root of 0? 0. Let's choose another x value that's less than 5. How about 4? What is the square root of 5 minus 4? Well, that's the square root of 1, which is 1. Should we plug in an x value of 3 into here? 5 minus 3 is 2. I don't want to take the square root of 2. What about plugging in an x value of, we didn't like 3, how about 2? Well, then we have to take the square root of 3. I don't love that. What if we plug in an x value of 1? What's 5 oh, I like that. The square root of 5 minus 1 means we're taking the square root of 4, and I know what that is. It's 2. See where I'm going with this? Choose convenient x values. Look at these y values that I'm getting out. Let's try to find one more. How about negative 4? Then we've got the square root of 5 minus negative 4, which is equal to the square root of 9, which is 3. I love it. All right, let's plot some points. Well, negative 4. Oh, good, negative 4 is on the graph. So an x value of 5 puts us at a y value of 0, plotting that point over there to the right. And, well, for you, the right's over there. What else? Oh, 4 comma 1 over 4, up 1. There we go. Over 1, up 2. And to the left, 4. See, there you go. To the left, 4. The negative tells us direction. It says to go to the left. And the 4 tells us how far to the left. So we're going to the left, 4, up 3. There we are. And then we could draw ourselves a curve that passes through these points. At least we could try. And our curve's going to look something like that, going off to the left there. I missed my second point there, but that's okay. You get the idea. This is the top half of a sideways opening parabola. It's a parabola that opens to the left, except we're only using the upper half of it. And we're only using the upper half because if we did include the plus or minuses, we'd have the lower half of this parabola, but that parabola would fail the vertical line test. It wouldn't be a function. We'd like it to be a function, so we're going to only use the top half of the parabola. And that's the process for graphing really any kind of a function that you don't just know what the graph looks like, is to take some convenient x values, plug them in, generate some y values, and plot some points. We did it. We made it to the end of this section, and it only took a delightful 54 minutes. Thanks so much for hanging with me on this one. I know that was a lot. It was a lot of content. Go back through your notes, organize your notes, take some little notes on the details that were in there. There was some pretty intricate stuff, and make yourself another section of your review packet that's going to help you be very successful on your next exam. And I will see you very soon. Thanks so much.